Hi friends, welcome to my channel. Let's have a look at problem 236, lowest common ancestor of a binary tree. So in this video, we're going to share two formats of solutions. So the first method is based on traversal in an iterative fashion, and the second method is a recursion method. So first, let's look at the requirement of the problem. So it requires us to find the lowest common ancestor, also known as LCA, of two given nodes in a binary tree. So the second paragraph here defines what's LCA. So let's look at the examples to gain some feeling. So in example 1, so the two nodes are 5 and 1. So their LCA is 3. And in example 2, so node 4 is a descendant of node 5, so we are going to return 5. So similarly in example 3. So the constraints or further assumptions are the following. So the number of nodes in the tree is in range 2 to 10 to the power 5. In other words, the tree is not an empty tree, and also it can have a number of nodes up to 10 to the power 5, a decent large number. So the third item is that all the node values are unique. So this is important. So the last two items are basically consistency assumption. It says that P and Q are different, and they are all also exist in the tree. So with that said, let's look at the method we're going to share. So the first method is a traversal solution. Here I'm going to use breadth-first search. So the idea is the following. So we want to find the root to node path, and then we locate the last same node in the two paths. So let's use example 1 for a demonstration. So if we want to find the LCA of 6 and 4, then we can first find the root to node path. For example, 3, 5, 6 is the root to node path for 6. Similarly, we can find the path 3, 5, 2, 4 for node 4. And then in this case, the last same node is 5, so we return 5. So this is method 1. So method 2 is based on recursion. So the idea is to use the definition of LCA. So what's LCA? So given P and Q, so we search from top to bottom or from root to subtrees. So there are two cases. So LCA is either P or Q if one is in the subtree of the other. So for example, the case in example 2. Or it's such a node such that P and Q lie in its two subtrees respectively. For example, the node 3, right? So 5 and 1 are in the two subtrees for this node, so we return 3. So after we share the code, we're going to make a comparison of the two methods. Let's first look at method 1. So this is based on root to node path. So for this, I'm going to split into two steps. The first one is going to get ancestor to node path, or from root to the node. So for this, I'm going to define a hyperfunction. Let's call it f. So from root to the node. So here we can assume that the tree corresponding to node is not empty due to the assumption that the number of nodes in the tree is in range greater or equal than 2, right? So it's not empty. So in here I'm going to use breadth-first search. So I'm going to first initialize a queue. So I'm going to use deck to mimic the behavior. So the queue will store node and the corresponding path ending at that node. So for example, root, and the path ending at the root is the root itself. So with that said, we are ready to do the while loop. So while queue. Then first I'm going to get the node and the path. So this is going to be pop left. So if we use pop left, we're using a queue behavior. Then first we are going to check if node value equals the go value. So let's change the function's argument a little bit. I'll call this one go. The go will be the P or Q. So let's see if node value equals go value. Then if this is the case, we're going to return the corresponding path. We're done. Otherwise, we're going to look at the subtrees. I'm going to first look at the right subtree, if node right. Then we're going to include the tuple corresponding to node right. So node right, and the path is path, then extend to the node right. So that's one. And next we're going to look at the node left. Then we're going to append the corresponding node left, and then extend the path to the node left. So that's the ancestor to node path. So next, I guess we are ready to make calls to this function and find the LCA. So let's see, call f and locate LCA. So for this, I'm going to introduce p path and q path. The p path will be the root to node p path. So I'll call root and p. And the q path will from the root to this node q. So once this is called, then we're ready to prepare the return. For this, I'm going to initialize a variable called result. His first state is none. Then I'm going to iterate. So for I and node 1, node 2 in enumerate zip p path and q path. Then first I'm going to set result equals n1. So if n1 does not equals n2, then it means that we first get the difference from the two paths. Then we're going to return p path I-1. So otherwise we return the result. So that's the solution 1. So let's do a special case check. Yeah, it passes one special case. Now let's do a generic case check. Yeah, it passes all the generic case. So now let's look at method 2. So method 2 will based on recursion. So let's copy this function signature and then call this solution v1. And now let's look at the second one. So this is going to be a recursion solution. And then we're going to use the idea here. So this what's LCA. Then we need to consider like this. So we start from if root is none, or root equals p, or root equals q. So in all these cases, we're going to return root itself. So it corresponding to the first line here, right? So then we're going to do the recursion call. So what we want to do is that, so we call the left subtree, so self lowest. Then the root will be root left, p and q, right? So basically this function, if we interpret as a recursion function, where what we are doing is to find where p and q lies, right? So this is right. So for example, self lowest ancestor, so root right and pq. And then we want to consider the first case is p, q lie in the two subtrees of root respectively. Then we are going to return the current root, because current root is LCA. So this corresponding to the this line in the understanding of LCA. So this case, so we're going to check if left is not null. So we're good. And right is not null. Then we're going to return root. Right. So as again, it's corresponding to the situation P and Q lies in the two subtrees of the current root. So we're going to return the current root. Otherwise, so it's either the left is null or the right is null. So else if left is not null, then we're going to return left. So this case corresponding to one is the offspring of the other. So actually, all the remaining cases after this if check is this situation. So we just need to determine which we need to return, left or right. So otherwise, we're going to return right. So the first case corresponding to the right is is an offspring of left, and similarly for the right. So I guess that's it for the second solution. Now let's do a special case check. Yeah, it passes a special case. Now let's do a generic case check. Yeah, it passes the generic case. So here, I guess, so both the two formats of solution actually are traversals. So here, this first one. So both are traversals in essence. So this is one thing. So another thing actually that might be interesting to know is that here in the breadth first search, I'm first calling the node right, then node left. The reason is that so you can change to call left first and then call right here. But if you consider pre-order traversal for binary tree, see, so in an iterative way, so the order is actually important. So we need to first call right and then left. So that's why we do this here. So it's good to compare this code with the binary pre-order traversal. So this is the second point. And the third point is that actually in the first solution, it's very useful to help us build intuition. So here is just an analogy. So if we consider the way we locate a delegate or representation of clusters in Unifund. So this is actually the similar thing. So we get to the node parent relation in the data structure in the Unifund or disjoint set first. So here, so using the parents and the offspring relation, so we can get the root. So this is also good to know. And with these three items mentioned, I guess that's about it for this video. Thank you very much.